Thank you for the invitation. And I'm Atsumi Niwa, leading the event-based sensor development at SONY. And today I will explain about event-based vision sensor and on-chip signal processing development. Sorry. Yeah. Here is today's contents, and first of all, I will shortly introduce our organizations and developed sensors, and then move to the presentation of the event processing development. This is operation of the event-based vision sensors, and I belong to the R&D team in Japan, and developed the EVS-related technology with Switzerland branch and broadcasting with the business team. And this shows three different generations of our prototyping with pixel shrink trend. And due to the complexity of the EVS pixels, the size shrink had been limited. But we tackled to achieve the small pixel with our using the warehouse stacking process and circuit technologies. This is our first generation EVS developed with Prophecies, and the feature is higher time resolution thanks to the asynchronous readout method, and it's suitable for the industry applications. This is our second generation with featuring technology of the small pixel size and low power consumptions. Because it is just a prototype, so the currently sensor consumes 70 milliwatt, but if redesigned, we can reduce to under the 10 milliwatt with keeping the 1000 frame per second operations. Third one is RGB hybrid EVS, which is configured by embedding high frame rate event pixel with low noise advanced mobile RGB pixels. And the simultaneous output is used for the image enhancement applications like Debra or the video frame interpolations. This is summary of our target applications, and three different sensors with different feature is suitable for the industries, mixed reality, and mobile imaging as listed applications. Then I move to talk about the event processing development. I will explain the motivations. Actually, the EVS is efficient sensors, but there are also the constraints to obtain the stable output. The one reason is detection threshold, and which is needs to be determined correctly. But second is some noise from the photons or the circuit, or the interference from the flickers. And we have developed auto threshold controlling processing and confirmed certain improvement. For example, the right top figure shows the example output with too high threshold, and we hardly detect any event. But after tuning the threshold properties, we can obtain the enough event, as you can see the left top figures. But in case of including the noise or the flickers, there is still low quality event after the tuning of the threshold property, as you can see from the left bottom figures. In recent days, lots of following the application is realized by using the neural networks, and if there is infinite computing resource and enough data set to train network, maybe this problem will be gone. But with considering the limitation of the available hardware or the computing latency or power consumptions, we still think more primitive processing with on-chip implementation is useful in some application field like mobile. So now we are focusing on the random noise and flicker suppressions, and we studied with three different approaches. And the first is filter-based denoise, including the three different algorithms. And the second is also the filter-based anti-flicker, both in the digital and analog domains. And the third one is relative suppression of the non-identities by enhancing the object itself. So I will explain each detail as follows. This is the denoise, and left figure is finding the noisy area by counting the event in blocks. And if the event number is less than the predetermined noise threshold, the event in the area is considered as a noise and removed. And middle figure, there is a calculation similar to the left figures, with defining the area as a surrounding of the events. And the right figure is applying the additional IIR filter to the left approaches. And we also think that it's important to set the proper threshold for noise distinctions. So we evaluate the false detection characteristic with no contrast input as an initial calibration sequence, and obtain the noise threshold table for each contrast threshold. This is anti-flicker processing, and the left side is digital domain approaches, and we are finding the period of the event stream. And if there is a periodical trend equivalent to the flickers, the event in the patch removed. And the right side is analog domain approach, and we are calculating the global flicker frequencies by convolution with internally generated flicker reference waveform. And if there is a flicker component, the detection threshold will be increased to suppress the detections. There's also two different object enhancement approaches, and left side is edge preservations, and we calculate the gradient with horizontal, vertical, and diagonal directions. And nominal object generates a decent amount of the events. Therefore, the event with weak gradient at any direction is considered as a noise. And right side is shoot template matching, and matching will be determined by comparing the previous and current frames number of the event in patch. So, for example, there is an isolated and blinking event between the frames. We can distinct such event as a noise. This is a measurement setup and methodology for quantifying the impact of the signal processing. And we are using the rotating object with radial patterns, and also defining the object area and noise area. And though it is not accurate, but we regard the event in object area as a signal, and also regard the event in noise area as a noise. Then we are evaluating the noise suppression ratio with comparing the event in noise area with turning on the processing, and after turning on the processing, the event is preferable to be reduced enough. And as a similar manner, we evaluate also the object preservation ratio with monitoring the object areas, and obviously the preservation ratio is preferable to close to 1. And this is the noise result, and as you can see, the filter-based approach shows a good result both in the noise suppression and object preservation ratios. And C1 of the edge preservation shows also a good characteristic in noise suppression, but the event from the object is also reduced. And C2 of the shoot template matching shows worse results. And we think the good result by using the filter approach is from the predetermined noise threshold through the initial calibrations. And also we can see the difficulty of the template matching. And when the object moves with keeping the direction and speed, the where matching is obtained at each local area. But in other words, there is a different trend in the peripheral side and center side of the rotating object. That is why the matching fails. Next is anti-flicker processing results. And we are putting the flickering LED near the object, and B1 of the digital filter-based approach shows the best scores. And as you can see, when we find the period of the flicker, the flicker suppression is well done. But on the other hand, there also happens to be unexpected period around the center of the object, so it causes block noise. And also, the other methodologies doesn't show the perfect result. So, I mean, the B1 of the analog-based approach, the higher threshold disturbs the object detection also, or the C1 of the edge preservation preserves the outline of the flicker light source also. So we need to choose carefully each algorithm with considering the impact from the such imperfection on use case. This is the last experiment with changing the scene light from the constant to the global flickers. And yes, we think that this is most problematic situations, and currently C1 of the edge preservation shows best so far. And though the shape of the object, especially at the circumference, changes, but noise from the flicker is well suppressed. On the other hand, the area-wise approach of the B1 and C2 doesn't work anymore, regardless of whether its area is fixed or the tap-based. Actually, the object becomes like a design art. Mm-hmm. This is a summary of our insight for the relationship between the requirement of the applications and the applicability of each algorithms. Actually, we think the best algorithm is dependent on each applications. So today, this table is just a hypothesis, but we will verify carefully each application with taking the available computational resource both on the sensor side and following application processor side into account to establish the optimized systems. That's all for my presentation, and thank you so much for your kind attention.